Hello everyone, good evening. Dinesh, hi. So we are in the session 10. So probably this one and one more session, right? We'll be able to wind up this laws of motion topic. Ridishri, hi. Okay, so where are we guys? We are in the applications of friction, right? We were actually looking at some problems or numerical types where we were using the concept of frictional force. Okay, so what we'll do is we'll start with some more warm-up questions on that, and then we will get into the idea of circular motion, because I think I would have told you that we have got the introduction to the circular motion when we have discussed about the motion in 2D. Again we are going to talk about the circular motion here. Again we are going to talk about the circular motion when it comes to work energy power, and also we will talk about the circular motion before we discuss the angular motion, because circular motion is a special type of angular motion. So in a way, right, you need to be prepared that the circular motion total concept, right, we are not going to do it in one place, we are going to do it like in 4 parts, because each of it will be relevant in one place. And if we try to do everything together in one place also, that is not going to be of much use. So that is the reason why we are going to split it and then cover the circular motion in these 4 parts. Already first part we have covered in the motion in 2D case. Second part of circular motion we will study here. Third part of circular motion we will study in work energy power chapter. Fourth part, right, which will involve derivations, etc., that we will do in the angular motion concept. Okay, so we'll just get started with some questions on the applications of friction. So look at this. In this figure, a block weight 60 newtons is placed on the rough surface. So we can see here, this is the block 60 newtons weight. So if the weight is 60 newtons, means we can see we are attaching a rope horizontal side, which means vertically, right, there will be the normal reaction and weight is given as what, 60 newtons. Vertically there is no motion, right, which means what, normal reaction will be 60 newtons. Okay, now read the question. The coefficient of friction between the block and the surfaces is 0.5. So block is here and the surface, right, what is the mu value? They are saying it is 0.5. I think I would have told you, if they don't mention whether it is the coefficient of static friction or kinetic friction, what we have to assume, for both of them the value is same. Okay, what should be the weight W? So here we are hanging a weight W such that the block does not slip on the surface. Okay, so here, just make one small correction. This is not just the weight W, it is the maximum weight W. So what is the question here? We need to find what is the maximum weight W so that the block does not slip on the surface. So what is happening? Just think intuitively, right, as we try to apply more weight, then obviously there will be a tension here. The tension will try to pull the 60 Newton weight block on the surface. The force that will prevent its motion is what? Frictional force. Here we need to find what? The maximum weight W, which will have this block does not slipping on the surface. That is what we need to find. Okay, already we got one result. What is it? The normal reaction between the 60 Newton weight block and the surface. What is it? 60 newtons. So from here we will have what is the frictional force limiting value. So we will take 0.5 as what? Coefficient of static friction. So frictional force limiting value will be what? Mu into normal reaction, right? That is what? 0.5 into 60, that is 30 newtons. Now look at the 60 Newton block, horizontal direction. There is a tension T1. Tension will be always acting into the rope. and there will be the friction. So tension will try to pull it to the left and friction will oppose it. Now if it should not move means what? T1 should be balanced by the friction. If it should not move means what? T1 should be balanced by the friction. Okay. What is the maximum allowed value for the T1? Because friction can attain the maximum value of limiting value, right? So the maximum allowed value for the T1 is what? The limiting value of friction, which is 30 newtons. This is the maximum allowed value for the T1. Okay, we'll just keep it like, equation 1. Now come to this junction point. Junction point, we have T2 here. Look at this. This angle also will be 45. So T2 cos 45 means 1 by root 2. T2 sin 45. Both are same, right? So that point should be equilibrium. If this block is not moving means the point also will be equilibrium, right? Which means what? Vertically there is a T2 into 1 by root 2 and weight W. These should balance means what? T2 into 1 by root 2 is equal to W. Horizontally there is a T1. We are looking at the junction point. T1 is to the right side. T2 into 1 by root 2 is the left side. They should also balance, right? So T2 into 1 by root 2 is equal to what? T1. We are looking at the balancing of the forces at the junction. So from these two relations, right? T2 into 1 by root 2 is equal to W. Also T2 into 1 by root 2 is equal to T1, right? Which means we can say T1 is equal to W. This is coming from the balancing at the junction point. Now, what is the maximum allowed value for T1 so that the 60 Newton block on the rough surface will be static? The T1, what is the maximum allowed value for T1? 30 Newtons. Which means for the equilibrium at the junction, we should always have T1 is equal to W, right? So the maximum allowed value for W will be when T1 is maximum. Which means what? The maximum allowed value for W will be equal to what? The maximum value of T1, which is 30 Newtons. So what is the answer for this? Option C. So here what they are asking, the maximum value for the W so that the 60 Newton block on that horizontal surface will be at rest. Is it clear, guys? So this is how we will be able to solve the question. So first thing is what? We have looked at the maximum allowed value for T1 by the equilibrium of the 60 Newton block. And then we went to the equilibrium of the junction. There we were able to find what is the relation, because we have to find the relation between T1 and W. From the equilibrium of the 60 Newton block, we are able to get the relation between the T1 value and the limiting friction. That is able to give us what? The maximum allowed value for T1 so that the 60 Newton block will be static. And then from the junction, we are able to get what is the relation between T1 and W. And that's how we are able to find what is the maximum allowed value for W. Okay. So this is how we'll have to approach this question. Next, look at another example. Again, this is also based on the applications of friction. An object is placed. It's a very standard question. In fact, no people remember this result, so that sometimes what happens is they can give, especially in mains kind of examination, right? They can give us questions where instead of keeping the parameters, like here we are putting theta, n like that, right? Instead of putting the parameters, they can instead give the values and frame a question. An object is placed on the surface of a smooth inclined plane, inclination theta. So it is kept on a smooth inclined plane. What is the angle of the inclined plane? Theta. It takes a time t to reach the bottom. Means if you take the length of the inclined plane to be L, how much time it is taking to slide down? It is taking a time t. It is taking a time t to slide down. Okay. This is a smooth. If the same object is allowed to slide down a rough inclined plane, so we are allowed to slide this object down on a rough inclined plane. It takes a time n times of t to reach the bottom, where n is a number greater than 1. This is something that we will generally see. If the inclined plane surface is smooth, right, the object will just come down fast. If the inclined plane is rough, it will take a longer time, right? That is what they are saying. It is becoming n times. The coefficient of friction mu, we have to tell this mu value in terms of theta and n. We have to tell this mu value in terms of theta and n. Okay. For this, what we will do is we will just take a look at the representation. So one smooth, other is what? Rough. So here also the length of the inclined plane is same, but here we have what? Friction. Now when you look at this is the smooth case, this is the rough. The component of weight which will be along the inclined plane is what? Mg sin theta. This is what is actually making the block to slide down the plane, correct? What is the acceleration coming because of that along the plane? We are looking at what is the acceleration along the plane. Remember, the only component of force which is along the plane will be mg sin theta, because normal reaction will be perpendicular to the plane. Weight is vertically down. We have taken the components of weight. Mg cos theta will be perpendicular to plane. Mg sin theta will be along the plane. Correct. Now the acceleration coming because of the mg sin theta will be what? Acceleration is what? Force by mass, right? Which is what? G sin theta. When we place the object at the top of the surface, we assume that this is starting from rest. It has to cover a displacement L. What is the acceleration? G sin theta. We need to find the time. Look at what is the relation we have. S is equal to what? Ut plus half at square, right? Means L is equal to Ut. U is 0. Half A is what? G sin theta into T square. Okay. So we will keep it as equation 1. How are we getting it? The displacement equation. S is equal to what? Ut plus half at square. Now this is done. Let us go to the this is over. The smooth case is over. We are able to get the relation. Let us go to the situation where we have the rough surface. When you have the rough surface, right, look at this. Here also we will have the component of the weight mg sin theta down the plane, but there will be a friction. Okay, so here since there is a motion, we will consider the friction as what? Kinetic friction. Remember, normal reaction will be what? Mg cos theta, because there is no motion perpendicular to the plane. So normal reaction is equal to mg cos theta. So frictional force is what? Mu into normal reaction, right, which is what? Mu into mg cos theta. That is the frictional force. Now it is going down, means net force should be down the plane. Frictional force will be upwards the plane. Mg sin theta is down the plane. So net force down the plane will be what? Mg sin theta minus mu mg cos theta. Okay. Then corresponding acceleration is what? We have to divide this by m, right? M will get cancelled. So what is it? G sin theta minus mu g cos theta. This is the acceleration. In the second case, what is the net downward acceleration? G sin theta minus mu g cos theta. So here also we are going to have the same displacement, right? Means what? Displacement is L is equal to ut. U is 0 plus half. Acceleration is what? G sin theta minus mu g cos theta into S is equal to ut plus half a t square. Here the time is what? Second case we are saying the time is what? Nt, right? Means we'll have nt square. Let us call it as our equation 2. So we have two equations here. First equation is coming from the motion of the block on the smooth plane. Second equation is coming from the motion of the block on the rough plane. Now it's more math. So we got the equations. From here we have to solve the equations. We have to solve the equations to get what is the expression for mu. We have to find the mu value in terms of what? In terms of n and t. So what we can do here, maybe we can just divide these two equations. Just do equation 2 by equation 1. Left hand side, what do we have? L. Here also L, means left hand side will be 1. Right hand side, what is this one? Half will be cancelled. T square will be cancelled. Then in the numerator we'll have what? G sin theta minus mu g cos theta into n square divided by g sin theta. Cross multiply. G sin theta is equal to g sin theta into n square minus mu g cos theta into n square. We'll just rearrange the terms. The negative term we'll bring to the left side, and we'll take the g sin theta to the right side. Mu g cos theta into n square is equal to what? G sin theta into n square is there. We'll have again minus g sin theta. Totally we'll take g sin theta common out. It will be what? N square minus 1. So from here we have to get the mu value, right? So what is the mu value? But before we get the mu value, we can cancel the g off. Then mu will be equal to what? The cos theta into n square will go to the denominator that side. It's equal to what? Sin theta into n square minus 1 by cos theta into n square. So check it guys, what is it? Mu will be equal to what? Sin theta into n square minus 1 divided by cos theta into n square. Okay. So now what is sin theta by cos theta? Here sin theta by cos theta is what? Tan theta. So I am writing out expression here. Mu is equal to what? Tan theta into n square minus 1 by n square. So this can be written as what? Tan theta into, if you split it right, n square by n square minus 1 by n square. That is what? Tan theta into 1 minus 1 by n square. So what is the answer? Option A. So here we need to clearly understand what are the steps we have taken. First, what did we do? We have started with the equation for the block on the smooth plane. Then we have looked at the equation for the motion of the block on the rough plane. We got two equations. Just we are doing mathematical simplification. Like, we divided both the equations. From there we are able to get what is the value of mu in terms of theta and n. What is the formula? Mu is equal to what? Tan theta into 1 minus 1 by n square. Like I said, this is a standard question, right? Tomorrow they can give a question saying, the angle of the inclined plane is 30 degrees. And initially the time is t. Finally the time is 2t. Which means what? The value of n is equal to 2. They can ask what is the value of mu for the coefficient of friction between the surfaces, like that. So if you remember, the standard result means we will be able to answer such questions just by substitution. Okay. So this is, broadly what we need to look at. I mean, when we say applications of friction, it can just go on. We can talk about variety of questions where we'll have the friction concept being introduced. Okay. But we have got some amount of practice. Maybe you can also take a look at the past year JEE mains as well as JEE advanced questions, so that you will be able to correctly know what is the expectation in terms of the JEE level questions. Okay, that you take a look at it, and if in case you are not able to solve some questions, we can discuss them. Okay, so this is about the applications of friction. Now we will get into the second segment of today's class, which is about the circular motion. So already we have had some discussion on the circular motion. What is it? When we have a particle which is moving in a circular path, it will have an acceleration towards the center. We call it as what? Centripetal acceleration, which is what? V square by r. If the centripetal acceleration is not there, then the particle cannot continue in the circular motion. If the speed is constant, then we will call it as what? Uniform circular motion. If the speed is also variable, then we will call it as what? Non-uniform circular motion. If the speed is not uniform means, then along with the centripetal acceleration, we will also have a tangential acceleration. Centripetal acceleration is responsible for what? It is responsible for the change in direction of motion, and tangential acceleration is responsible for what? Change in the speed. Tangential acceleration is responsible for what? Change in the speed. Okay, so this is something that we have already discussed. And tangential acceleration will be what? Rate of change of speed. Okay, so these are the things that we have talked about with regard to the circular motion, correct? Now here what we are going to do is, if a particle has to go in a circular motion, then we are saying there should be compulsorily acceleration towards the center. We are calling it as what? Centripetal acceleration. Means what should be the corresponding force? There must be a force acting on the particle, right, towards the center. The corresponding force will be given by what? Mass times acceleration, right? What is it going to be? M into V square by R. So this much force should be acting because of some source. Here what we'll do is we look at some examples where we will try to understand how the circular motion is achieved by the source force. Basically, we need to have some force that is able to provide this centripetal acceleration. Here we look at some cases where the centripetal acceleration is met by the known forces that we already discussed so far in the chapter. Okay, so in this, right, we have a very important example, that is taking a turn on the road. Because when you're taking a turn on the road, right, like you can see, if you're taking a turn on the road, it is like what? For that small part where you are taking a turn, it is like you are going in a circular path. And to go in a circular path, right, we should be having an acceleration towards center of the circle. Otherwise we cannot go in the circular path. Otherwise we will not be able to take the turn. So what kind of forces are there that will practically help us in taking a turn? That's what we will discuss, and it's a very standard topic when we have the applications of friction. So look at it. If you have a horizontal road, so there is a horizontal road and we are trying to take a turn on the horizontal road. This is the top view. What you're seeing is actually the top view. Okay, now let us look at the side view. When you see it from sideways, this is how it will look like. So there will be weight acting on the car or vehicle, whatever you take, that will be downwards. There will be the normal reaction. Vertically there is no motion, right, which means what? The normal reaction is equal to mg. Now if we are trying to take a turn, there should be a force that will be acting towards center or right, otherwise the turn will not happen. So here the force that will help in taking the turn is static friction. What is the force that will help in taking the turn? Static friction between the road and tires of the car. So why are we saying static friction? Understand this carefully. If the car is trying to take a turn, it should have a force towards center. If it is not having a force towards center, what will happen? The car will try to move away from the circular path. Means it will have a tendency to skid. If the center of the circle is towards the left side, imagine like here, then if the force is not there to enable it to get the centripetal acceleration, then car will try to skid away. So thereby the friction comes into play. The friction will be what? Static friction. It will try to stop the skid. The static friction will now be acting towards the center of the circular turn. And here, right, if we need to have a safe turn means what? Look at this. What is the centripetal force that is required for us? mv square by r. This much force is required for us. Okay, where r is what? The radius of the circular turn. Static friction should be able to provide this, which means this is the required amount of force. This should be less than or equal to what? The limiting value of the static friction. What do you mean by limiting value of static friction? Mu s into normal reaction, right? But what is normal reaction already? Mg. Means mv square by r should be less than or equal to what? Mu s into mg. So mm we can cancel. From here what do we have? V square should be less than or equal to mu s into rg, or V should be less than or equal to root of mu s into rg. So this is the safe velocity or safe speed. Means if our speed is less than or equal to root mu s into rg, right, we will be able to take the circular turn on a horizontal road. If not, what will happen? Think about it. If you are going at a, so that is the reason why whenever you go to some turns, right, they will mention that the speed limit is 30 km per hour, speed limit is 40 km per hour, like that they will mention. Okay, so if we go with a higher speed, what is the common observation? Tell me. We will skid, correct or not? We will be skidding. Okay, so look at this, the safe speed. What is the safe speed formula? Maybe we can just make a note of it. What is it? The safe speed should be less than or equal to what? Root mu s into rg. Mu s is what? Coefficient of static friction. We have to keep one thing in mind. The friction that is enabling the circular turn is what? Static friction. Mu s is the coefficient of the static friction. R is the radius of the circular turn curvature. G is what? Acceleration due to gravity. While doing our derivation, we have taken capital R. In this formula, we are putting it as smaller. Does not matter. R is what? Radius of curvature. Okay. Now, if we have a vehicle which is speeding at a higher value, then you try to take a turn. What is the practical observation? We will see that the vehicle will be skidding away. This is a very practical observation that we do. Now, why the vehicle always skids away? It will not be skidding towards the center of the circle. It will be skidding away. Why? You know, when the vehicle is skidding away, what is going to happen? Just imagine. The radius will increase. When the vehicle is skidding away, what is going to happen? The radius is going to increase. And you will also see, like in the F1 race and all that, if suddenly they are taking a turn, it might skid for some time and then it will stop and then keep going. The skidding will actually stop after some time. Why does it happen? Think about it. When the skidding is happening, the radius is increasing, right? If the radius is increasing, look at this. This mu s into rg value will increase. Other things are constant, right? Only varying thing is r. When radius is increasing, mu s into rg value will increase. It will increase in such a way that you will again meet this condition. You will meet the condition that the velocity is again becoming less than or equal to root mu s into rg. Initially, the velocity is higher, but as the radius is increasing, right, mu s into rg term value will increase. So skidding will stop when the velocity value is again, see, initially we have the velocity as, say for example, 40 km per hour. In this case, the mu s into r1g, this is not sufficient. The root mu s into r1g is not sufficient. Okay, but as the radius is increasing, we will get the value as what? Radius will be increasing, right? So we'll have root mu s into r2g now. The value of r2 is more than r1, such that now we'll have the condition that this 40 km per hour, right, will be less than or equal to root mu s into rg. Okay, so that is how the skidding will happen, and why the vehicles will also stop after skidding for some time, because we will also have a doubt, right? It should keep skidding forever. After skidding for some time, it will stop and then again it will keep going in the circular path. Why? The reason is this. So what is the important result here? The safe speed. if you want to just take a circular turn on the horizontal road, what is the safe speed we need to have? The V value should be less than or equal to root mu s into Rg. Okay. Now sometimes, right, the road may be smooth, especially we cannot have a really rough road in Formula 1 track and all that. They cannot have a rough track, right, because that might cause a lot of other problems. So you may be required to have a smoother road. Smooth means what? Mu s will be less. Then our safe speed values will be very, very low. If you want to have a V value less than or equal to mu s into Rg means what? The safe speed values will be very less. Then how will we be able to move the vehicles? In those cases, right, there will be one more technique, which is what is called as the banking. What is the technique that is used? Banking. Okay. So like this, we will see normal road also when you have turning. If you go to the Ghat road, like if you go to Tirupati and all that, you will see the turning, right, they will just have lot of elevation of the road. So like you can see in this here, right, what is it? There is an, so this is the horizontal, right, this is the horizontal, this is the road. So they have elevated it, they have basically elevated the road. This angle, right, is what we'll generally call as the angle of banking. So we'll see that the circular turn can be also enabled by the banking concept. Banking means what? Elevating the road on one side is basically called as what? Banking. Okay. Now we can see one more example here. This is how so this is the horizontal. You see, the banking is very high here. The banking angle is very high. Okay. We cannot have very large value of banking, because that might even what? Tilt the vehicle, right? You see, almost if you are actually sitting in the bus means you will get a feel that you are about to tilt sideways, right? So we cannot keep on increasing the angle of banking also, but we'll see how the banking will actually help in taking the circular turn. So if you look at, this is what we have, the road surface. You can see this is what? Elevated. This is the normal horizontal. This angle is theta. See, normal horizontal, perpendicular to it is the normal reaction. If you tilt the road by angle theta, normal reaction also will be tilted by the same angle theta. If you tilt the road by an angle theta means from the vertical, initially if the road is horizontal means normal reaction is vertical, right? If you tilt the road by theta, normal reaction also will be tilted by the same angle theta. You can see here, this is how normal reaction will be, making an angle same theta with the vertical. Now when we take the components of normal reaction, right, one component is vertical component, n cos theta. What will be the horizontal component? N sin theta. The car will not move vertically. Car will not be able to move vertically. Okay. So which means what? N cos theta is equal to what? Mg. And horizontally, this n sin theta, right, the component of the normal reaction, this is what is going to meet the centripetal force requirement. Means what? N sin theta is going to meet the centripetal force requirement. Means what? mv square by r. R is what? Radius of that circular turn. From here itself, let us say this is maybe equation 1, equation 2. We'll just do equation 2 by equation 1. What is there on the left hand side? So n will be cancelled. Left hand side will have sin theta by cos theta. That is equal to what? Right hand side, mv square by r divided by mg. Mm is cancelled. V square by rg. So sin theta by cos theta means what? Tan theta. Tan theta is equal to what? V square by rg. So here we are getting what? The angle of banking required. If you are having a vehicle which is moving with a velocity v, okay, and you want to take a circular turn with some radius of curvature, then for that value of v and r, what is the required angle of banking? Tan theta will be equal to what? V square by rg. So this is another important result. What is it? Tan theta is equal to V square by rg. And from here we can also find what is the speed. that will correspond to the given angle of banking. Like, if you already have a road which is having an angle of banking and radius of curvature, then for that, what is the corresponding velocity the vehicle can have? Look at this, just cross multiply. What do we have? Rg into tan theta is equal to v square, means the corresponding v is what? Root Rg tan theta. What is the corresponding speed? It is root Rg tan theta. So we will also call it as what? The safe speed. So if you already have the road which is already banked with some angle of banking, and we have the circular turn radius already fixed, then for that configuration, what is the safe speed we can have? V is equal to what? Root Rg tan theta. If you go with this speed, means we will be able to have the circular turn safe. Okay, and here the centripetal acceleration rate is provided by what? It is provided by the component of the normal reaction. It is provided by the component of the normal reaction. But think about it, practically when you look at most of the roads, when you go to the turning right, they will give you a banking angle. Slightly the road will be tilted on one side. Okay, and there will be of course friction also, which means there will be the banking involved as well as friction. Now what we do? We have discussed them separate. First we have seen what is the role of the friction to provide that circular turn when we are taking a turn on the horizontal road. Now what we have seen, the role of banking which helps in taking a turn. Practically what we'll see both of them. So when we are looking at a circular turn on a road, we will have the friction involved as well as the banking also. Now here look at it now. So we have elevated the road by angle theta as we discussed before, right? The normal reaction will make an angle theta with the vertical. Like we did, we can take the components. What is the vertical component? N cos theta. What is the horizontal component? N sin theta. What is the required centripetal acceleration? V square by R, correct? Now here we have shown friction to be acting down the inclined plane. We have shown friction to be acting down the inclined plane. But friction is what? The static friction. We know static friction is what? It's a variable and self-adjusting. So here it is not like friction is going to be always down the plane. Friction can change its nature. So if you look at what will be the direction of the frictional force when the velocity with which we are trying to take the turn is more than root Rg tan theta. Remember the banking, what is the safe speed? Root Rg tan theta, right? If the velocity is more than that, means what? The component of the normal reaction rate will not be able to provide the centripetal force, because centripetal force will be what? M into V square by R, right? The normal reaction component will not be able to provide the centripetal force here. Why? Because V is more than root Rg tan theta, which means we should have some more force component which is towards the center of the circle. How that will come? Because if the friction is down the plane, imagine, then we can resolve the friction into components, right? Look at this. The components of friction will be what? F cos theta will be towards the center of the circle. F sin theta will be vertical. So when we are taking a turn with a velocity more than root Rg tan theta, right? Then we will require one more force component which will be towards the center. Then only we will be able to meet the centripetal force requirement. So friction will be acting down the plane. If V is exactly equal to root Rg tan theta, this is what we discussed before, right? In the previous case, what is it that we discussed? If we have a velocity which is exactly equal to what? Root Rg tan theta, then what we have? Just the normal reaction component itself is able to provide the centripetal acceleration. So there will be no tendency for the car to skid. If there is no tendency for the car to skid, means the frictional force will be what? Zero. Friction force will not even be there. What if the velocity with which we are trying to take the turn is less than root rg tan theta. Means now the component of the normal reaction is more than the required value of the centripetal force, which means what? In this case, the vehicle will have a tendency to skid down, means it will have a tendency to go towards the center of the circle. To prevent it, right, the friction will be acting exactly in the opposite direction. Because if the vehicle is trying to skid towards the center of the circle, right, then the friction will try to oppose it, means friction will be acting up the plane. So this is about the way in which the friction is going to act. But now the interesting thing for us is, what is the maximum speed we can have? Like say there is a road which is having a banking and there is a friction also. On this, what is the maximum speed with which I can take a circular turn? This is what we will be more interested. If we are looking for what is the maximum speed with which we can take a circular turn, right, then for this we should have the maximum possible forces that are towards the center of the circle. Because if I am looking at the maximum speed to take the circular turn, means our centripetal force requirement value is going to be highest, which means what? We should have as much force components towards the center of the circle. That means what? We will have, of course, the n component, which is n sin theta, that will be towards center of the circle. Also we will have the friction down the plane, so that the friction horizontal component, which will be what? See, this is theta, means this will be 90 minus theta, and hence this will be theta. F cos theta will be towards center. So both n sin theta and f cos theta, both of them will be acting towards center, means they will support the centripetal force requirement. Okay. And another component of f is what? F sin theta, which will be down. So we have taken the components of both the normal reaction and the friction. Look at this. If you just represent the forces alone, right, what do we have? The horizontal components towards center of the circle. N sin theta is there, f cos theta. Vertically we will see n cos theta will be vertically up, f sin theta is down, mg is also down. So here vertically there is no motion for the car, right, which means what? N cos theta is equal to what? F sin theta plus mg. Okay. Horizontally, that is where we have our centripetal force equation. What is the total force towards center of the circle? N sin theta plus f cos theta. This will be providing that centripetal acceleration, means that will be equal to what? The centripetal force requirement, which is mv square by r. Here we are trying to have the maximum value for v. When the maximum value for v will come? When our friction is the highest, right? When the maximum value for v will come when the friction is having the highest value. What is the highest value for friction? Means if you take mu s as the coefficient of static friction, then the friction maximum value, because we are talking about the limiting, what is it? Mu s into normal reaction. The friction value will be equal to what? Mu s into normal reaction. Okay. So for us to have the maximum velocity for taking the turn, the friction must be corresponding to what? The limiting value of static friction. Okay. So here what we'll do is, in both the, let us call it as equation 1 and equation 2. In both the equations we'll substitute friction to be what? The limiting value. So n into sin theta plus mu s into n into cos theta is equal to what? mv square by r. So here you can see that n we will take common. N we will take common, what do you have? Sin theta plus mu s into cos theta is equal to what? mv square by r. Okay. Now here we will bring this to the left side. N cos theta minus f will be what? Mu s into n sin theta is equal to mg. Here also we will take n common out. Cos theta minus mu s into sin theta, that is equal to mg. Maybe we can call it as equation 3 and equation 4. So from here, right, whatever the v we are going to get, that is going to be what? The maximum velocity which we can have and still achieve the turn. What is the v that we are going to get from here? The maximum velocity which we can have to take the turn on this particular road, which is banked and which is also having the friction. Now what we'll do is we'll just do equation 3 divided by 4. We'll do equation 3 divided by 4. So look at this. Here left hand side n will be cancelled. Sin theta plus mu s into cos theta divided by cos theta minus mu s into sin theta. That is equal to what? Right hand side mv square by r divided by mg. So this is what? V square by rg. Okay. So now we are going to get a very standard result. This is a very important standard result that people will remember. So what we are going to get is the maximum velocity which a vehicle can have and take a turn on this particular road. So look at this. What do we have? Sin theta plus mu s into cos theta divided by cos theta minus mu s into sin theta. That is equal to what? V square by rg. Now left hand side what we will do is let us divide both numerator and denominator by cos theta. Numerator denominator divided by what? Cos theta. So here we will have what? Sin theta by cos theta, which is tan theta. Here we will have cos theta by cos theta means 1. So mu s. Here what is it? Cos theta by cos theta means 1. Here sin theta by cos theta means mu s into tan theta. That is equal to what? V square by rg. So which means rg we will bring it to the left side. It will go to the numerator. Rg into tan theta plus mu s divided by 1 minus mu s tan theta. That is our V square. What is this velocity final value we are getting? V square is equal to what? Rg into tan theta plus mu s divided by 1 minus mu s tan theta. This is what is V square. What is this? This is V square. Okay. So if you are looking at V value means it will be what? Root of that. So we have to take a square root on both sides. So look at this. The maximum value of the velocity which we can have and still take a turn safely. What is it? Root of. So we'll have to take a root on both sides. That will give V max. So what is V max? Root of Rg into tan theta plus mu s divided by 1 minus mu s tan theta. So in all these discussions, right, sometimes we are using capital R, sometimes we are using small r. We should keep in mind that both are referring to the same thing. What is it? The radius of circular turn. Both are referring to the same thing. What is it? The radius of the circular turn. Okay. So what is this expression for the velocity? It is what? V max is equal to what? Root of Rg into tan theta plus mu s divided by 1 minus mu s tan theta. Okay. So it's a very standard result that we need to remember. Then you would have seen, like, you know, when the cyclist, when they are taking a turn, right, they will exactly try to use this. They will actually bend the cycle. When they're taking a turn, you will see that they will be bending the cycle. So when they bend the cycle, what happens? Look at it. The normal reaction will be like this, right? So you will have a component of the normal reaction, like the way we discussed. There will be a component of the normal reaction. So this is theta means n sin theta. And of course there will be the friction also. So they will try to achieve both these objectives. Like they will try to achieve the component of the normal reaction as well as the friction in order to have a safe turn. Like, you know, you would rarely see that people are holding the cycle upright and then taking a turn. generally what do we see? They will actually bend. Like if I'm taking a turn to the left, they'll actually bend the cycle towards the left. Like you see here in this diagram, right? They're taking a turn like this. That's why they're bending it like. So whichever way you are trying to take a turn, right, you will intuitively you will bend it so that you will be able to take advantage of this fact. You will have the component of the normal reaction supporting us in providing the centripetal acceleration and also friction. Okay, so this is about the cyclists taking a turn. Then the other very interesting example of this circular motion is death well. I'm not sure if you happen to go to this circus and all that, right, which comes if you happen to be in Chennai, like near that, you know, Chennai Central, sometimes they will keep this circus. So in circus, one of the very popular things is this death well. Like you'll see the guys, they may go in the death well on a bike, or sometimes they may even use a car. And generally what happens is the people who are like the visitors will be staying at the top. So if you really appreciate their efforts, means sometimes people will put a cache like this, and they will not only be riding that bike, but they will even catch this cash and then they will put it in their pocket. Okay, so maybe if you really happen to go to these things, you will be able to understand what I'm talking about. Okay, but what actually happens because of which these guys are not falling down? See, the death well will not be like a very small place, right? It will be like some 20-30 meters height. These bikers are almost flat. You can see they are horizontal. Why they are not falling down? We'll see why they are not falling down. So look at this. If you see the way the bikers are riding, so you see that they are almost like flat. So the normal reaction, you can see here, normal reaction acting on them, right, will be horizontal. Normal reaction is the one that will provide the centripetal force requirement. Okay, so the normal reaction will be equal to what? mv square by r. Normal reaction is going to provide the centripetal acceleration, which means what? Normal reaction will be equal to the centripetal force requirement, which is mv square by r. Now if you look at the vertical side, there are two forces. One is because there will be weight that tries to pull them down, right? The friction between the tires of the vehicle and the well will be acting upwards. It will be a static friction. Okay, and if there has to be a balance, otherwise they will fall down. If there has to be balance, means what? The frictional force should be able to balance mg. The frictional force should be able to balance what? mg. Okay, now for the frictional force to be able to balance this mg, right, the mg value should be less than or equal to the limiting value of the friction. Mg value should be less than or equal to limiting value of friction, right? Which means what? What is this limiting value of friction? Means mu s into the normal reaction. What is the normal reaction here? mv square by r. So we can see m will get cancelled on both sides. Okay, so what we'll have? The g should be less than or equal to mu. Here mu means we're talking about the static friction coefficient, mu s into v square by r. Okay, so again from here, right, what we will get? R will go this side, so rg by mu s, that should be less than or equal to v square. Means what? V should be more than or equal to root of rg by mu s. Means the biker, right, should always have a velocity. If the velocity is not there, means he will not be able to go in this kind of motion. So what is this? We call it as what here? The safe speed. For him to go in this death well, right, the velocity should be more than or equal to what? Root rg by mu s. So what we call it as? We call it as the safe speed for going in this death well. If he is not maintaining this speed, right, which means what? he will have the danger of falling down. If suddenly, God forbid this should not happen, but suddenly if they are there and their engine is stuck, then what they will cleverly do is that they will try to go down in a spiraling kind of a path. If they don't go down, means what happens? They will just fall off because of the gravitational force. So if the velocity is not maintained, velocity should be always more than or equal to what? Root rg by mu s. Okay, so this we call it as what? The safe speed. So the v value should be more than or equal to root rg by mu s. So minimum we will be requiring is what? Root rg by mu. Okay, it should be more than or equal to this value. So this is what we call as the safe speed in the death well. And here the frictional force, right, is balancing the weight so that they are able to go in the, so essentially, you know what they will do? They will be essentially going in a horizontal circle. Why they are able to go in a horizontal circle? Because the weight is balanced by the friction. And for that, what is the minimum speed that they require? Root rg by mu. The velocity should be more than or equal to root rg by mu, but minimum is what? Root rg by mu. This is what we call as the safe speed of the death well. Now, when you are going in a bus or a vehicle, it happens practically that the road, right, will have some curvature. So typically what you see like this, an up bump. This we can think of it like what? A convex. Bulging outwards is called as what? Convex, right? A convex. You tell me, when you are going in a car and you are getting a bump like this, not a small one, but a portion of the road, then we will generally get a sense that our normal reaction is actually decreasing. Normal reaction means we will not know normal reaction, we will feel that the weight is decreasing. Because weight is decreasing means we are referring to normal reaction. Why it happens, we will see. If you are on this convex kind of a bridge, right, look at this, weight is down and our center of the circle is also down. Net force towards the center means what? Mg minus n1, that is equal to what? Mv square by r. Means if you rearrange, means Mg minus Mv square by r, that is n1. So we'll see, normally if you are going on a flat road means what? Normal reaction is equal to Mg, right? But here what we are having, normal reaction is Mg minus something. So we'll actually feel that our weight is getting reduced. That's what, I mean, we also normally observe. On the other hand, what we can also have is this concave type of bridge. Look at what is this concave type of bridge. We'll have a curvature like this. If you're going in the concave type of bridge, right, look at this. The center will be somewhere here, center of the circular term. Means we have to look at what is the net force upwards. N2 minus Mg is equal to what? Mv square by r. So take the Mg to the right side. N2 will be equal to what? Mg plus Mv square by r. So here what do we observe? If we are getting into a concave type of bridge, right, what do we get? We'll get a sense that our weight is increasing. Weight means we are referring to what? The normal reaction. We'll get a, feeling that the weight is increasing because what actually is happening? The normal reaction will be increasing. So this is another practical observation that we'll do when we are going on a road. So if we have a convex bridge, means what do we observe? We'll observe that the weight is kind of decreasing. It's not the weight is decreasing, it's like what? The normal reaction will be getting reduced. If you go in a concave type of bridge, means it will be what? Increasing. Okay. Now another important arrangement with regard to this circular motion is this conical pendulum. So we'll talk about this again when we go to oscillation chapter. So conical pendulum means you'll have the rope, pendulum rope, making an angle theta. So you'll have the bob of the pendulum. A is like the bob of the pendulum. Okay. So it will go in a circular term. Now here if you can see, right, tension will be here. Theta is the angle. So if you see the angle here is theta. So T cos theta will be up. T sin theta will be horizontal. So vertically there will be no motion for this pendulum bob, which means what? T cos theta will be equal to Mg. Why is it coming? Because of the vertical balance of forces. And horizontally there is T sin theta. This will provide the centripetal acceleration. Means T sin theta will be equal to what? mv square by r. T sin theta will be equal to what? mv square by r. Okay, so let us call it as what? Equation 1, equation 2. We will do equation 2 by equation 1. So T is cancelled. Left hand side will have sin theta by cos theta. Right hand side will have mv square by r divided by mg. Mm is cancelled. V square by rg. So tan theta is equal to what? V square by rg. So this is the relation between what? The angle of the conical pendulum and the velocity with which the bob will move and the radius of the cone. So cone will have a base radius, right? R is what here? The base radius of the cone. Okay. So this is the relation we have between the theta value and V as well as the base radius of the cone R. So we'll talk about the conical pendulum again when we go to the oscillation chapter, but this is another case of discussion for the circular motion. Okay. So broadly what we have seen in this session is the important one, the enabling of circular turn because of the friction, because of banking, and because of both friction and banking together. Okay. And then we have seen some special cases, the death well, and then we have seen the convex bridge and concave bridge. Why do we feel little weightlessness when we go on a convex bridge, and we'll feel heavier when we are going on a concave bridge? That also we have seen. Why is it? Because of the normal reaction changing. And then the last one of course is the conical pendulum. Okay, so these are some of the examples that we can think of in terms of understanding the centripetal force, how the centripetal force is provided by the common type of forces that we are aware of. Okay, in the next session what we'll do is we'll talk about the idea of inertial and non-inertial frame of reference. Okay, because that's something that we have not covered so far, and that is something which people would feel like it's a little bit of an additional topic. Why? Because any problem which we are able to solve by using the idea of non-inertial frame, we'll be able to understand what I mean to say by a non-inertial frame when we go to that session. But I'm just giving you a head start so that you will be able to probably look at that topic. So any problem we can solve by using the non-inertial frame method can be solved also by using the general approach that we have used so far, which is what we call as the inertial frame approach. Okay, so we'll discuss about it when we go to the next session. Okay, and probably with next session, right, we'll be able to wind up this chapter. So just make sure that you practice the previous year questions, both JEE mains level as well as advanced level on this. Okay, we'll see in the next session.